Shikimic acid is not a direct antiviral compound. It is a precursor in the synthesis of oseltamivir, the primary active ingredient in Tamiflu. At the molecular level, shikimic acid contains a cyclohexene ring bonded with multiple hydroxyl/OH groups, forming a three-dimensional structure that functions like a flexible chemical scaffold. This configuration allows chemists to attach additional functional groups, ultimately constructing a molecule capable of inhibiting the influenza virus enzyme neuraminidase. Neuraminidase acts like a key that enables newly formed viruses to escape from infected host cells. When this enzyme is blocked, the virus cannot spread efficiently. The mechanism resembles locking the gates of a fortress during a siege. You may not eliminate the enemy immediately, but you prevent their movement and expansion. Remarkably, nature concentrates the highest levels of shikimic acid not in the seed, but in the fruit's outer layer, the pericarp. This reflects an evolutionary strategy. The fruit's outer shell serves as a chemical defense barrier, protecting the seed from microbes and insects. The plant did not produce shikimic acid for human medicine. It produced it for self-preservation. Humanity merely discovered this biochemical fortress and re-engineered it for its own purposes. When global demand for Tamiflu surged in 2005, the world confronted a sobering reality. Synthesizing shikimic acid entirely in the laboratory was extraordinarily complex and expensive. The plant's own biosynthetic route, known as the shikimate pathway, proved far more efficient than any industrial production line. Long before entering pharmaceutical laboratories, star anise had existed for thousands of years in traditional East Asian medicine. In classical Chinese and Vietnamese medical theory, it is categorized as a warming herb, believed to regulate vital energy, qi, and warm the body's core. From a modern physiological perspective, the essential oil of star anise, rich in anethole, stimulates TRPV1 and TRPA1 receptors in the oral cavity and stomach. These receptors respond to heat and pungent compounds. When activated, they create a warming sensation and promote localized blood circulation. Interestingly, the traditional concept of warming may correspond to measurable physiological processes, such as increased peripheral blood flow and modulation of the autonomic nervous system. Thermal homeostasis, the regulation of body heat, is not merely a matter of temperature, but also of neural perception. In centuries past, before antibiotics or antiviral drugs existed, medical systems relied on accumulated observational knowledge. Star anise was used to relieve abdominal pain, reduce bloating, and support respiratory function. Today, we know that certain compounds within it possess mild antimicrobial and smooth muscle antispasmodic properties. Not every ancient belief withstands scientific scrutiny, yet they were not random assumptions. They emerged from thousands of years of practical, real-world experimentation, a form of pre-modern clinical trial. Approximately 80 to 90% of the world's star anise production is concentrated within a narrow geographic corridor: southern China, northern Vietnam. This is not merely an agricultural statistic, it is a geopolitical variable. Star anise requires a humid subtropical climate, along with soil possessing specific pH levels and mineral composition. It cannot be scaled as easily as staple crops like rice or corn. This ecological specialization creates a form of natural monopoly. In 2005, as demand for Tamiflu surged, the price of star anise rose sharply. Governments began to recognize the fragility of the supply chain. A strategic antiviral medication depended on the harvest of a single plant species, grown in a limited geographic region. Supply chain vulnerability does not apply only to semiconductor chips or crude oil. It exists in botany as well. This situation pushed scientists to explore microbial fermentation methods capable of producing shikimic acid using genetically engineered bacteria. Biotechnology has reduced reliance on natural harvests to some extent. Yet the fundamental lesson remains: no matter how advanced pharmaceutical manufacturing becomes, it remains deeply interconnected with agricultural ecosystems. And when a pandemic emerges, Maps of forests and mountain ranges can become just as important as maps of laboratories. Not every star is safe. There is a species that looks almost identical, in shape Elysium anisatum, commonly known as Japanese star anise. To the naked eye, the two species can appear nearly indistinguishable, but their chemical compositions differ profoundly. Elysium anisatum contains anisatin, a compound capable of stimulating the central nervous system and triggering seizures. At the molecular level, anisatin interferes with GABA channels, the brain's primary inhibitory signaling system, disrupting the delicate balance of neural communication. The same eight-pointed shape, on one side, a precursor that helps save lives. On the other, a neurotoxin. This is not merely a story about plants. It is a lesson in botanical mimicry, the way morphological similarity can conceal profound chemical differences. In nature, form does not always reflect function. For the pharmaceutical industry, an error in raw material identification can lead to catastrophe. That is why origin verification and chromatographic analysis serve as protective fortresses, safeguarding safety and efficacy. Star anise is not magic. It did not cure a pandemic on its own, but it reminds us of something fundamental. Modern civilization is not separate from nature. It is an extension of it. Every antiviral capsule may begin with a sophisticated synthetic reaction, but deep beneath that process lies an ancient biological pathway that has existed for hundreds of millions of years. We did not invent shikimic acid. We merely learned how to read its code. In your kitchen, a dried star anise pod may simply flavor a pot of pho, but in a laboratory, it once became the starting point of a global antiviral strategy. And perhaps the greatest lesson is not about chemistry, but about humility. Our high-tech civilization still depends on small wooden stars growing quietly in the forest. In 2005, inside emergency meeting rooms at the World Health Organization, epidemiological maps of H5N1 were projected onto screens like battlefield charts. Nations stockpiled masks, experimental vaccines, and an antiviral drug called Tamiflu. Yet few noticed a quiet detail to synthesize Tamiflu's key active ingredient. Laboratories did not begin with steel, silicon, or industrial polymers. They began with a dried, star-shaped fruit. In the humid mountain forests of northern Vietnam and southern China, Illicium verum was silently producing a precious molecule, shikimic acid. The modern world, with its supercomputers and global supply chains, suddenly found itself dependent on an ancient biological code written by plants. The question is not only how does star anise help create medicine, it is also why must our advanced technological civilization still borrow its solutions from a tree?